This slideshow will introduce you to key concepts in rock deformation. In order to describe deformation, you need to understand two words with specialized meanings: stress and strain. Stress is what deforms materials. It's the intensity of force, the force divided by the area over which the force is applied. A knife works because it focuses the force you can apply with your arm onto a very narrow edge with a small area. Thus the stress, which is the ratio of force to area, is large and can deform or slice something like a carrot. Strain is just a fancy term for amount of deformation. The key property of strain is that it can be quantified. That is, we can say that something has more strain than something else, and we can say by how much. For example, the circle is progressively strained to a higher and higher degree in these drawings. We want to understand how rocks deform when subjected to stress. The easiest way to understand the different behaviors is to plot these two variables on a graph. The vertical y-axis will be the stress, the thing that tries to deform the rock, and the horizontal x-axis will be the strain, the amount of deformation caused by the stress. The origin represents zero strain and zero stress. In other words, a rock just sitting there. The first style of deformation we can demonstrate on this graph is elastic deformation. The blue ball represents an elastic object. When you click on the blue box, the ball will deform, and you can see the state of stress and strain recorded on the graph with the red dot. You can replay the animation as many times as you want. The key feature of elastic behavior is that the ball rebounds to its original state when the stress is released. It behaves just like a rubber ball. When you squeeze it or apply stress, it deforms, but when you stop squeezing or release the stress, it springs back. It's that springing back that causes an elastic material like a rubber ball to bounce back to you off the ground. All elastic materials have a limit to the degree they can be deformed. If you try to deform them beyond this point, they break. This limit is called the yield strength or elastic limit, and the breaking is called brittle failure. Here you can see the same elastic ball, but this time it will deform until it reaches its yield strength, and then it will break. Once it's broken, you can't put the pieces back together again. The deformation is permanent. Click on the blue box to see how an elastic material deforms when it reaches its yield strength. The yield strength is the maximum amount of stress that the material can tolerate before it breaks. It's a value on the y-axis. There are many different kinds of elastic materials. Some are strong, meaning that it takes a lot of stress to cause a small amount of strain, and some are weak, which means that a small stress can cause a large strain. Some have high elastic limits and some have low elastic limits. Here we show two materials, a strong one in blue and a weak one in pink. Click on the boxes to see how they deform. Notice that the strong material makes a steep slope on the stress-strain diagram, which simply means that for a given amount of stress, it doesn't deform very much. The weak material, in contrast, makes a shallow slope because a given amount of stress produces a lot of deformation. The second important style of deformation is called ductile deformation. Ductile deformation is permanent. The material doesn't rebound when the stress is released. Click on the blue box to see the blue ball deform in a ductile fashion. Notice that when the stress is released, the red dot, which indicates the state of stress and strain, simply drops vertically to the x-axis. This is because during this phase the stress is decreasing, but the strain isn't changing. Lots of common materials have ductile behavior, like clay. The last type of deformation you need to know is fluid deformation, when material flows. The key property of a fluid is that it will deform infinitely in response to any stress, no matter how small. As long as the stress continues to be applied, the fluid will continue to deform or flow. Click on the blue box to see an attempt to illustrate fluid behavior on the stress-strain diagram. It's actually hard to do because the stress needed to start the fluid flowing is tiny, so it can scarcely be shown above the x-axis. And the fluid continues to deform forever as this tiny stress is kept at its tiny value. It's because of this response to stress that fluids will always take the shape of the container they're in. Gravity provides the stress that continues to move the fluid until a completely flat surface is reached, at which point there is no more driving stress. You will be able to see this demonstrated in the Silly Putty slideshow. Here's the point. Rocks, just like trees, can display brittle behavior. Rocks can break and do so along faults, producing earthquakes. And, just like Play-Doh, which is a classic example of ductile behavior, rocks can be bent too. Most of us don't think of rocks as being ductile, but as this photo attests, rocks can and do bend. Finally, rocks can flow too, as seen in this movie of Hawaiian lava. It's important to remember, however, that rock can flow without turning into a liquid by melting. This is that odd property of the asthenosphere that makes plate tectonics work. It's a solid rock that deforms ever so slowly in response to any stress. So it's a fluid, albeit a very stiff one. Scientists use the term viscosity to refer to the sluggishness of a fluid in response to a stress. Remember, fluids will always deform in response to a stress, but the rate of deformation or flow varies with the fluid. Fluids with a high viscosity, like the asthenosphere, deform very slowly, while fluids with a low viscosity, like water,